Last year, we spent a little bit of time talking about area between curves and volume. And this year, we're going to go into a little more depth, especially in the volume section. But it's good to review area between curves. So we'll spend 2 days on this. So let's just jump into this first problem and remember how we did this. So we're going to need to draw this region. So we have e to the x is an exponential function. And y equals x is a line which lives totally below e to the x on the interval from 0 to 2. So we are looking at, let's make this more colorful, this little region here is the region that we're trying to find the area of. Okay, it might be better. Let me make my exponential function grow a little bit faster. Just so we can see, there we go. That's probably more correct. They don't live quite so close to each other. So we have something like this. So now we're trying to find the area between those curves. And if you remember from last year, what we would do is we could do top curve minus bottom curve, because essentially what we're doing is we're finding the area under e to the x and then subtracting out the area under y equals x. So we had an integral of top minus bottom. And we're going to do this integral in terms of x because remember the way that we determine that is by drawing either vertical or horizontal line segments and seeing which one makes more sense in terms of the function on the top and bottom or right and left staying the same. So here, if I draw vertical line segments, the top function is always the curve e to the x, and the bottom function is always the curve x. So we do our integral in terms of x. The reason that drawing vertical line segments gives us an integral in terms of x is because, whoopsie, we're really thinking about these line segments as being tiny little rectangles. And so it's like we're adding up the area of infinitely many little rectangles. And the width of each rectangle is a change in x values. And that's where the delta x is coming from. So that's the easiest way to remember that. Vertical things correspond to x. So our x values go from 0 to 2. So this is the integral that gives us this area. This one's fairly easy to anti-differentiate. 0 to 2, so we plug 2 in, we get e squared minus 1/2 times 4 minus e to the 0 minus 0. So when you type this into a calculator, you get 4.389, remembering that e to the 0 is 1, not 0. Okay. So try this next one. Again, start with the graph. So 2x squared is a parabola. And 1 minus 2x squared is an upside down parabola. That's slightly shifted upwards. And so the region that we're looking for the area of is this one here. Again, I can draw vertical line segments. My top function is always the blue graph. And my bottom function is always 2x squared. Here's your top minus bottom. And now I have to figure out my bounds. So I need what are these x values? So that's where those two curves intersect. So we'll set those equal to each other. Add 2x squared to both sides. Divide by 4. Take a square root, so we get plus or minus the square root of 1/4, which is 1/2. So this will be negative 1/2. This is positive 1/2. So my integral goes from negative 1/2 to positive 1/2. And I'll let you guys do the work in anti-differentiating, but you get 2/3 there for that area. Okay, there's more on the next page. So now this one is one where if I look at horizontal or vertical line segments, for this first one over here, the top function and bottom function are both the blue graph, which is kind of interesting. For this line segment here, the top and bottom functions are both those black lines. And then over here, the top function is the black line, the bottom function is the red line. So if we wanted to do this integral in terms of x, we would have to break this up into at least 3 different integrals, which is not pretty. So let's try sideways, things that go on the side. We notice if we do this, the right function is always the red function, and the left function is always the blue function. So we can do this integral in terms of y. because we're using horizontal line segments. Remember when we do things in terms of y, we do right function minus left function because that's what will give us a positive value. And so we want our integral just to have y's in it. So my right function is e to the y, and my left function is y squared minus 2, making sure to put parentheses around that. And then my y values go from -1 to +1. So -1 to +1. I'll let you anti-differentiate this. We get 5.684. At this point, we care more about just setting up the integral than doing the integral, although this one's pretty easy to anti-differentiate. Okay, so one more to do on this video. So we have ln of x. X equals 0 is the y-axis. Y equals 0 is the x-axis. And y equals 1 is a line up here. Okay, so the region that we're looking at here is this one. Looking at the region that's bounded by all 4 of those curves. Okay, so again, if I try horizontal or try vertical line segments, for those first few, the top function is the blue function, the bottom function is the red one. But then over here, now I have the top is blue, but the bottom is black. So I would have to do at least 2 integrals if I wanted to do this in terms of x. But if I do this in terms of y, the function, sorry, that was supposed to be y equals ln of x. Y equals ln of x is always my right function, and the x or the y-axis is always my left function. So doing this in terms of y makes sense. So we're going to do right minus left. Okay. My left function is the y-axis. That's where x equals 0. So that's just going to be 0. My right function is y equals ln of x, but remember my integral is supposed to have y in it, so we need to rearrange this. To get rid of the ln of x, I do e on both sides, so I get e to the y as x. So I have e to the y, and then I'm going to integrate from 0 to 1. Okay, this one's super easy to anti-differentiate. Just e to the y from 0 to 1. So e to the first minus e to the 0. This gives us 1 point something. I'm just going to leave it like that though. Okay. Hopefully this all is coming back to you from last year. If not, let me know in class and we can talk in more depth about this.